Hi guys, this is Mr. Lakin. I'm going to be doing Unit 8, part of Unit 8 with you. The Unit 8 is such a big unit that we're dividing into two parts, Part A and Part B. I'll be doing the first part with you. Ms. Logus will be doing the second part with you. This unit is going to be mostly about polynomial functions for the first half. It's also going to be a little bit about rational functions for the first half as well. So we'll go ahead and get started. The target here is to be able to sketch a polynomial curve using all these different components, and you should probably read this on your own. Be familiar with all that vocabulary. And in case you were freaking out when I said be familiar with all this vocabulary, we're going to go over all this vocabulary in this video in case you're not sure of any of it. Here we go. Find a polynomial function that has the given zeros, x equals 0 and x equals 2. The way we'll do that is we'll take x and set that equals 0, the given information. We'll also let x equals 2. Now here's a trick that we've never done before. And I just subtracted 2 from both sides of the equation. This part I'm going to do over here is going to seem a little bit silly. I just subtracted 0 from both sides of the equation. I think that deserves an ooh and an ah. I didn't hear anything. I didn't hear anybody say ooh and ah, so I'm going to go ahead and go on. If you remember the zero product property, it said that if you set a factor equals 0 and solve for x, then that's going to be a root. I was given the roots. I actually put it back into a factored form. So to find the polynomial function that has these zeros, all I have to do is put these two factors together, which is x minus 0 and x minus 2. And I'll set that equal to y. And there you go. That's a polynomial function that satisfies those conditions. Now, I could also be tricky, and I could say that another polynomial could be this one. And I'm going to call that y2. I'll call this one y1. Now, is this satisfy the conditions? Well, let's find out. If I take x minus 0 squared, let me change the color here. If I take x minus 0 squared and set that equals 0, x does equal 0. And if I take x minus 2 and set that equals 0, I do get out x equals 2, which is what I was supposed to get. In fact, there's an infinite amount of polynomials that you could make. It's just that the exponents for them might be a little bit different. End behavior is kind of a tricky concept, but not terrible. Take this graph, for instance. And you're welcome to draw this on your own page as well. The ends of the graph are here, a start and an end. This part could actually be classified as a cubic function or an odd function with a positive coefficient. And you're thinking, Mr. Lakin, what in the world are you talking about? I'm tired. It's already 4 minutes into the video. I'm falling asleep listening to your voice. If you thought that I just fell asleep listening to my own voice, you're correct. So here's what's going on. I'm going to make a nice handy chart, and I'm going to relate it back to that little graph that we had. The left side of the graph, the degree, there's two options. You can have an odd degree, and you can have an even degree. The lead coefficient, you can also have two choices. You can have a positive lead coefficient or a negative lead coefficient. Now, here's how it all kind of works together. If you have an odd degree with a lead coefficient, your end behavior looks like what I just drew. If you have an odd degree with a negative lead coefficient, your end behavior looks like that. And this is always true. For any polynomial with an odd degree and a negative coefficient, your end behavior will always have these two arms, left side up, right side down. For an even degree, like x squared, we can expect the arms to both be up. And for an even degree with a negative coefficient, that means that the arms will both be pointing down. I'm going to take this piece here, and I'm going to translate that into words. We're going to erase this picture. I'm going to draw a new one. So for a polynomial like x to the fourth, negative, plus x squared plus 4. I don't know what this quadratic looks, what this fourth degree polynomial looks like, but I do know that I see a negative coefficient with an even degree, and a negative coefficient with an even degree has arms pointing down. And I don't know what goes on in the middle here. I really have no idea. That part, who knows? But I do know that, again, the arms, the ends, have to be pointing down. The last thing I'll say about this is that if you want to translate this into words, we could say as x goes to negative infinity, or to the left, the y values are going to be going down to negative infinity. And as x goes to positive infinity, or to the right, the y values are still going in that negative direction. This is how we would translate this concept of end behavior into mathematical notation. The number of turns. So here's a random and arbitrary polynomial, and you'll notice that it turns twice, right there and right there. The way we find the maximum number of possible terms, and I said terms there, I meant turns with an N, is the degree minus 1. So, if I have x to the fifth minus 3x squared plus 2, again, I really don't know what that polynomial looks like, but I can find the maximum number of possible terms could be 5 minus 1, which is 4. I'll also note here, not only could this polynomial have 4 maximum terms, it could also have 4 extrema, maximum. For real zeros. If I take a polynomial, and you're probably thinking, Mr. Lincoln, where are you getting all these polynomials from? In my head, I'm making them up. This is what I do in my spare time. For this polynomial, it's a fifth degree polynomial, and that means that I could have a potential 5 real zeros. Now, 5 possible real zeros, that means that, generalizing this idea, that the number of real zeros, possible real zeros, is equal to the degree of the polynomial. I keep saying the word possible. X to the fifth, this polynomial, x to the fifth minus 3x squared plus 4x minus 5, may not actually have 5 real zeros. It might actually only have 1 real zero. But I can expect, anytime I look at a polynomial, that the maximum number of possible real zeros will never exceed the actual degree. Finally, adding on to this concept is the concept of multiplicity. And I just realized that writing in red looks really angry, so I'm going to go and change the color to a happy color, like black. A multiplicity. Let's take this random polynomial. It's going to be in factored form as x minus 2 and x minus 5 squared and x plus 4 to the third. If I was to graph this, the roots would be at a 2, at a 5, and at negative 4. Because I would take this polynomial and I would set each of these factors equal to 0 and solve for x. The degree of this polynomial is going to be x to the first, times x squared times x cubed, so the degree is going to be a 6. And the lead coefficient, since all these x's just have a 1 in front, will be 1. I have an even degree with a positive coefficient. That means my arms will be pointing up for an end behavior. Here's where the multiplicities come in. Multiplicity means that a factor is going to appear more than once. X minus 2, there's only one of them, so the multiplicity of x minus 2 is 1. For x minus 5, the multiplicity is 2, and for x plus 4, the multiplicity is 3. What that does to the graph is the following. When I approach negative 4 for this root, the graph ends up going through the x-axis. Now it also does a funny little dance because of the cube, but the point is that the graph is going to go through the x-axis. Now at some point it's going to bounce back up. We don't know where that is. That's going to take some more math knowledge to know, and we don't really care at this point. When we get to 2, because 2 has a multiplicity of 1, the graph is going to go through the x-axis. And finally, for the root of 5, because the 5 has an even multiplicity, the graph will go back down at some point, and when it reaches x is 5, the graph will bounce and head back up again to positive infinity. This is a sketch only. I want to be aware, you would be aware of that. And I also bring your attention to that I'm really just interested in you understanding the concept of even and odd. The even ones, even multiplicities, will bounce at the x-axis, and the odd multiplicities will go through the x-axis. This is a page where you should stop the video and just read on your own. It's information that was taught to you previously. Here's an example where we're going to tie all this information together. The degree of this polynomial is 4. The lead coefficient is 3. We have a positive lead coefficient. We have an even degree. Arms will be pointing up. And you can reference that chart from the previous page to make sure you know what I'm talking about. The terms, there's 2 of them. And we said for the end behavior, since the arms are pointing up, as x goes to the right, so as x goes to the right, the y values are going up to positive infinity. And as x goes to the left, the y values are going to positive infinity. Please check with your teacher if they want you to know this part in a sentence or just the general idea of where the arms should be on a graph. Possible extrema. Since we had a degree of 4, the maximum possible extrema is going to be 3, because we always subtract 1 from the exponent. The number of possible zeros is going to be 4, and please add in the word real. Finally, the values of the real zeros, let me just get this equation, will be the following. Factor this. We can take a 3x squared out of both parts, and we get x squared minus 2, and we'll set that equal 0 because we're trying to solve for the x-intercepts. This part, we'll get x equals 0, and if you solve this and set it equals 0, this factor, you'll get x equals plus and minus root 2. The y-intercept, plug in 0, and you get 0, 0. Combining all this information on the graph, we had a root at 0, 0. Let me get the marker going. We had a root at 1.4, which is the square root of 2. And we had a root at negative 1.4. And you're going to notice that this is going to be a terrible graph because of how close the x values are. When I connect this all together, I had a odd multiplicity for negative root 2, and even multiplicity for 0, and then the graph goes back up.